National 5. So starter today, 5 questions. I want you to pause the video, and then once you've finished, unpause it because I'm just about to go over the answers. Okay, so question 1, what type of bond is found in lithium? Well, you need to know that lithium's a metal, so that means it's going to be metallic bonding. Okay, explain how metals conduct electricity. So you've got the delocalized electrons. So delocalized electrons make up the sea of electrons, and that sea of electrons allows electricity to pass through it. Okay, so delocalized electrons make up the sea of electrons where electricity can pass through. Okay? Right, 3A, copy and complete. You need to know your reactions with metals. Okay, so we've got a metal plus oxygen, we've got a metal plus water, and we've got a metal plus acid. So a metal plus oxygen gives us a metal oxide. So in this case, sodium plus oxygen will give us sodium oxide. Calcium plus water gives us a metal hydroxide, so that's calcium hydroxide, and we also get hydrogen. Okay, we get hydrogen gas. And then the last one, a metal plus an acid always gives you a salt plus hydrogen, and to name the salt, you take the metal, magnesium, and you change the acid like what we did when naming salts and acids and bases. So that would be magnesium nitrate, and you're also getting hydrogen. Yeah, H2 hydrogen gas. How can we test for the gas made in C? Okay, so how do we test it? It burns with a pop. Okay, hydrogen burns with a pop. And you need to know that, so important. Okay, question 4, what type of reaction takes place when we extract metals from their ores? We went over this, it's reduction. Okay, reduction. And then question 5, what method do we use to extract gold? Now, if we look at the Electrochemical Series, we'll see gold's away down at the bottom, so it's not very reactive. Yeah, the higher you are, the more reactive it is. So gold's not very reactive, so it doesn't take a lot to separate it. So heat would be enough. Okay. Now aluminium, we go gold, mercury, silver. After silver, we need to start using heat with carbon or carbon monoxide. So for copper, lead, tin, nickel, iron, and zinc. But when we get to aluminium, it's too reactive. It wants to be in its ore, so we need to use electrolysis for aluminium. Okay, we are going to go over that in a wee bit more detail today, but just you should know that, electrolysis. Right, so what we're going to do now, we are going to do our second lesson on metals, and we're going to continue our extraction of metals. Okay, extraction of metals. I introduced it last lesson. Last lesson we'll sort of recap, and then we'll go into just a wee bit more detail. Okay, so as I said, everything above silver and below aluminium, so copper, lead, tin, nickel, iron, and zinc, heat's not enough. Okay, so we would use heat plus carbon or carbon monoxide. Okay, so copper, lead, tin, iron, and zinc all need extracted with heat plus carbon. Extracted with heat plus carbon, or you can use carbon monoxide. Okay, carbon or carbon monoxide, it doesn't matter. Due to being more reactive than silver, but not as reactive as aluminium. Okay? And you need to know that. You need to know that order. Okay? So I'll go through that one more time. Gold, mercury, silver, they're not very reactive, so they only need heat to extract their metals from their ores. Copper, lead, tin, nickel, iron, zinc, a wee bit more reactive, so they need heat and carbon or carbon monoxide. And then aluminium and above, these are your really reactive metals, so you need to extract the metal using electrolysis. Okay? That's why these metals weren't discovered until electricity was discovered. So, let's carry on with electrolysis. So, aluminium and above require electrolysis to extract the metal. Okay, electrolysis to extract the metal. Now, hopefully you already know what electrolysis is because we did it in Unit 1, but we'll go over it again. Electrolysis is the breakdown of an ionic compound, okay, a metal and non-metal, so an ionic compound back into its elements. Okay, so we take an aluminium compound like copper chloride and we split it back into copper and chlorine. Okay, and we do that using electrolysis. So electro meaning electricity and lysis meaning to break up. Okay, now what's important here is that a DC current has to be used, and we spoke about this at the time, okay, but this is just a recap. So DC current must be used to ensure permanent positive and negative charges at each electrode. Okay, that's why we're using a DC current, a direct current. Okay, so we always have a permanent positive electrode and we always have a permanent negative electrode. Okay, and as we answered in the starter, spoke about it last lesson, extraction is a reduction reaction. Okay, it's a reduction reaction. So what that means, we are going to go into it in a wee bit more detail today, but it means an ion gains electrons to form an atom. Okay, and what we mean by that is if in the case of aluminium, aluminium's ion is Al3+, because it's in group 3, 283, it loses 3 electrons to become Al3+. So if it's getting reduced, if it's undergoing a reduction reaction, it gains 3 electrons to become an atom. Yeah, aluminium and it's solid at room temperature. Okay, that's what we mean by reduction. The ion is gaining electrons to form an atom. Okay? Right. What we're going to look at now is we are going to look at displacement reactions. Now we did this in third year, okay, but it is a National 5 outcome, so displacement reactions. Hopefully you can remember it, or if you don't remember it, hopefully it starts to make a wee bit more sense as we go through it, okay? So displacement reaction, this is when a metal higher in the electrochemical series. Now, we spoke about the electrochemical series last lesson. That's found on page 10 of the data booklet. Yeah, page 10, the electrochemical series. Now, I'm going to be writing this quite a lot. Okay, so I'm not going to write out electrochemical every single time. So this is when a metal higher in the electrochemical series. I'm just going to call it the E series from now on. Okay, but when you're writing your answers, make sure you write out electrochemical series. Okay, so this is when a metal higher in the electrochemical series displaces. Now, what we mean by displaces, hopefully you can remember, it means kicks out. Okay, and I'll explain what that means. So it displaces, it kicks out a metal lower down from its solution. That's what we mean by displacement. So when a metal higher in the electrochemical series displaces a metal lower down from its solution. Right, what we mean by this, if I give you an example, if we take zinc, yeah, that's a metal, and we react it with copper sulfate solution, yeah, what's going to happen if I show you the electrochemical series? If we find zinc, zinc's up here, yeah? Copper's down here. Now, because zinc is higher than copper, what's going to happen is that the zinc is going to kick, or it's going to displace the copper out of the solution. So this then becomes zinc sulfate solution plus copper. Okay, and that's it. That's displacement. Now, if we reverse this, if we start with copper and we have zinc sulfate solution, I'm just going to put aqueous solution. Now, again, look at our electrochemical series. Zinc's up here. Copper is down here. Because copper isn't higher than zinc, it can't displace it. So when that tries to kick the zinc out, it can't. So this reaction actually doesn't happen. Okay, because the copper isn't higher than the zinc to kick it out of the solution. Okay, and that's very important. So let's make a wee note. So talking about that one. So that reaction does not work as copper is not higher than zinc. So therefore cannot kick out. But if we want to be scientific about it, we do use the word displace. It cannot displace the zinc in solution. And that is literally it. Okay? So the rule. You already know the rule, but let's just get it cemented. So metals higher in the electrochemical series will displace metals lower in the series. Okay, so metals higher in the electrochemical series will displace metals lower in the series. The opposite can't happen. Metals lower down cannot displace metals higher. Okay, so let's do some examples. I'll do the first one. So iron plus gold nitrate. Now, will this reaction happen? Let's see. Let's find iron. Well, iron is up here. Gold is down here. Yeah, it's not very reactive, gold. So iron, because it's higher than gold, the iron will displace the gold. Okay, so it will kick it out. Let me just... Yeah, it will go like that. So this then becomes iron nitrate plus gold. Right, the next two I want you to do. Okay, so potassium plus copper sulfate. Is that going to work? If so, write the products. And then number 3, tin plus lithium sulfate. Is that going to work? If so, write the products. You can pause the video if you want, because I am just about to go over the answer. Okay, so potassium plus copper. If we look at our electrochemical series, yeah, copper, the one that's in solution, copper sulfate, that's down here, and then the potassium is higher up. Okay, so because the potassium is higher up, it will displace it. So this becomes potassium sulfate plus copper. Okay, and then the last one, tin is trying to kick out lithium, so tin's down here. Lithium though is higher up, so because the one that's in solution, yeah, the lithium sulfate, because that's higher up, the tin won't be able to kick out the lithium because it's not higher in it, so this reaction won't actually happen. Okay, now just a wee note, because I know I have spoke about it, but I've not gave you the note on it. Metals higher in the electrochemical series, okay, metals that are higher in the electrochemical series are more reactive. Yeah, they're more reactive. Metals lower down like gold, mercury, silver, they're not quite reactive. In fact, they're barely reactive. But metals higher up, certainly your potassium, lithium, sodium, very reactive, very reactive. Right. Now, what we're going to do now is, I know we've been speaking about it, but we are going to look at the electrochemical series in a wee bit more detail, okay? And because I'm going to be writing it quite a lot, I'm going to shorten it to the E series, okay? The E series. Now, again, we've covered this in third year, so hopefully, you might have forgotten, but hopefully it all starts coming back to you as I go through it. So we are going to look at oxidation. Yeah, what do we mean by oxidation? Oxidation, this is the loss of electrons. Okay, so an oxidation reaction is when we get a loss of electrons. So what we mean by that is we have magnesium atom, yeah, solid, and that loses 2 electrons, yeah, to become magnesium 2 plus in solution. Okay, so the magnesium is an atom. It's got the electron arrangement 282. It loses 2 electrons to become stable, and then that makes it Mg2 plus. Okay, so the reason this is oxidation is because the electrons have been lost. They are on the right hand side of the arrow. Okay, so any electrons on the right hand side of the arrow means they've been lost. Okay, Now, the next one we need to look at, and we already know this because extraction of metals is this reaction, it's reduction. Okay, so reduction, if oxidation is the loss of electrons, reduction is the gain of electrons. Okay, so what do we mean by that? I'm going to take this equation, yeah, and essentially we're just going to flip it. So this is when you would have Mg2 plus ions, and it's gaining 2 electrons to form the atom Mg solid. Yeah? So you'll notice that the electrons this time are on the left of the arrow. Okay? So if they're on the right, the electrons have been lost. If they're on the left, the electrons have been gained. Okay? So what we can do is we can use the E series, the electrochemical series, to find out the reduction equations. Okay, so that's page 10 of the data book. We already knew that, but I'm just giving you the note. Okay, so we can use the electrochemical series to find out the reduction equations. So page 10 of the data booklet, here are all the reduction equations, and you'll notice that every single one, the electrons are to the left of the arrow. Okay, and that's because in reduction equations we are gaining electrons. Okay, we're gaining electrons. So, for example, if we look at zinc, yeah, if we look at zinc on our data book, zinc, the reduction equation is Zn2 plus aqueous plus 2 electrons gives us zinc solid. Okay, so we can write that. So Zn2 plus 2 electrons, and that is going to give us Zn solid. So the Zn2 plus has gained electrons, so it's became an atom. Yeah, so it's underwent a reduction reaction. We would say that the zinc has been reduced. Okay, the zinc ion has been reduced. Now, if I pick another one, let's go for calcium. Yeah, if we take our data book again, calcium's a wee bit higher up, but the reduction equation, we just write it as it is. Sorry. So that would be Ca2 plus in the aqueous state, plus 2 electrons gives us calcium in the solid state. So that's Ca2 plus aqueous plus 2 electrons goes to calcium in the solid state. And that's how we write the reduction. Okay? So all these equations, so all the equations in the electrochemical series, all these equations are reduction equations. Okay? It's all about gaining electrons. Okay? Well, all these equations are reduction equations. It's all about the gain of electrons. They're so important. Now, sometimes you need to write the oxidation equation. So to do this, so to write the oxidation equation, we flip. Okay, so to write the oxidation equation, we flip the reduction equation. Okay, So I'll take the calcium one. So if I go for calcium 2 plus aqueous, that's gaining 2 electrons to become an atom. Okay, that is your reduction equation. So what we need to do, yeah, get the arrow directly underneath, like that, and then basically you just want to, whatever's on the right, you put on the left, and then the two that are on the left, you put on the right. So this becomes Ca solid goes to Ca2 plus 2 electrons, and that is your oxidation. Okay, and that's it. So that's all we're doing. We're taking the reduction equation and we're flipping it. Okay, so the product now becomes the reactant, and the reactants now become the products. That is all we are doing. I'll highlight that just so you can see it clearer. Okay, so the product, we flip it, it becomes the reactant. Yeah, the reactants flip and become the products. And that's it. That's how you get the oxidation equation. So you take the reduction and you flip it to get the oxidation. Now, we'll call that example 1. Let's do example 2, just so it makes sense. If we find lithium, okay, so lithium's at the top, so it's Li plus aqueous plus E minus goes to Li solid. Okay, so Li plus aqueous plus an electron goes to Li solid, and that there is reduction. Okay, now all we do, get the arrow directly underneath, and then we flip it. So the two products, the two reactants become the products. And then the product becomes the reactant. Okay, so again, I'll highlight that for you so you can see that. So the product becomes the reactant, and the reactant, or the reactants, become the products. And that there, because we've flipped the reduction equation, that is the oxidation equation. So oxidation is the loss of electrons, remember, the loss of electrons. So I'm going to summarise this. There's a way to remember it. Now you would have done it in third year, but to remember it, it is oil rig. Okay, oil rig. Now oil stands for oxidation is loss, and the rig stands for reduction is gain. Okay, so oxidation is the loss of electrons, okay, and reduction is the gain of electrons. Yeah, oil rig. That's how we remember it. Okay, oil rig. Oxidation is loss of electrons, reduction is gain of electrons. Oil rig. Yeah, so let's summarise what we've done today. So we recapped on extraction of metals. So gold, mercury, silver, they only need heat to get extracted. Anything between silver and aluminium, so copper, lead, tin, nickel, iron, zinc, that requires heat plus carbon monoxide. And then anything above, aluminium and above, requires electrolysis. Okay, you need to know that electrolysis is the breakdown of an ionic compound back into its elements using electricity. And why do we use a DC current? Yeah, to ensure a permanent positive and a permanent negative charge at each dipole. Okay, and we also spoke about how extraction is a reduction reaction, and we've now learned that reduction is the gain of electrons. Yeah, rig, reduction is gain. We then started talking about displacement reactions, yeah, and the whole rule about displacement reactions is here, yeah, I might actually highlight that, because it is important, is that metals higher than the electrochemical series will displace metals lower than the series. So, this one here, iron, because iron is higher than gold, the iron will displace the gold, and this becomes iron nitrate plus gold, yeah. This one here, tin plus lithium sulfate, this is your solution. Because tin isn't higher than lithium, it can't displace it. Okay, so because it can't displace it, no reaction happens. Yeah? And then finally, we learned a couple of new terms. Oxidation is the loss of electrons, reduction is the gain of electrons. Oil rig. Yeah? Now, to get the reduction reaction, you just write exactly what it says in the data booklet. So for lead, that would be Pb2 plus 2 electrons Pb solid. Yeah, if the electrons are on the left or to the left of the arrow, it's reduction because we're gaining those electrons. Now, to get the oxidation, what we do is we flip it. So we take the reduction reaction. So for calcium, we take the reduction reaction and then we flip it. The reactants become the products become the reactants. Okay, that's so important, especially when we start going into redox. Okay, it's so important. Okay, right, we're going to post some work on Teams, but that's us for today in terms of YouTube, so thank you.